We're going to take a look at this problem. If the rope is drawn towards motor M at a speed of 5t to the 3/2 meters per second, where t is in seconds, determine the speed of cylinder A when t is 1 second. So we have this picture here, and we have our, we want to measure all of our cable lengths. So let's say this length from here to here, we can call that B. Remember, we can ignore anything that like wraps around these outside of the pulley because this length is going to be constant. There's always going to be that amount around the outside of the pulley. Same thing here. We can ignore this half down here, and we can ignore this little piece over here. And now we can call this B. I call that B because it's just going to be constant. Notice this is going to be constant because this pulley's not moving. This pulley's not moving. So that length there is going to be constant. So I'll sort of note that constant. And if this is our cylinder A, we want to know the speed of that. And so now this pulley is going to move at the same speed of A, so we can consider that is going to where we're going to get our velocity for A. And now notice something interesting here. This length, and this length are all the same. And they're going to be changing at the same rate because these pulleys up here are fixed. So these three pieces of the cable are going to move it uniformly as this pulley moves up and down. So they're all going to be called by the same length. I'll call these SA. So this will be SA length. This will be SA. This will be SA. And again, they have to all be measured from a fixed point because this one's moving, but this one right here is fixed. So that's legitimate. Now over here, we'll call this length going into the motor, call that SM. And that's measured from this point here, which is also fixed. Now it says we want the velocity at t equal 1 second. So I just use the velocity equation we were given and put a 1 in there. So the velocity of this right here, maybe call this Vm for motor, is going to be 5 meters per second. So find the length of the cable. So we have 1, 2, 3 times 3A plus B plus SM. I think I was originally going to give that a different name, so we call that B here. So the total length of our cable is going to be a constant, and it'll be 3 times A. That gets this one, then add this one B, add this one SM equal to some L, and that's going to be constant, that L. So take derivative with respect to time, and just take the derivative. Of course, since B was constant, that's going to be 0, and our total length of the cable is constant, that's going to be 0. And of course, this is the velocity of A. This is the velocity of M. So we can replace those with that. And now we're just about done. We're going to plug this, our velocity, into here. I just plugged our given velocity into here. So when we solve this, VA is going to be negative 5/3 meters per second. Now, if we look at what this means, again, VA is the velocity of this length A. So the negative means this length is getting shorter. So if it's getting shorter, that means A is moving up by this amount. So A moves upward at 5/3 meters per second. I left off some things here. Excuse me. So I plugged in 5 here. Our velocity, I got VA is equal to negative 5/3. And again, since it's negative, this is getting shorter. These cables are getting shorter, which means A must be moving upward. So A moves upward at 5/3 meters per second. So let's take a look at this problem here. And let me just see if I can. There we go. So take a look at this. The end of the rope moves downward with a speed of 5 meters per second. Determine the speed of cylinder B. And now one thing to notice, we have two different cables here. There's going to be this one right here. It's kind of a short one. This one right in here. And then we have the other one that kind of goes all the way around. So let's take a look at this. Yeah, so this short one here was this one right here that kind of goes all the way around here. And then the long one is this one goes around here. And so let's mark these in some way. Let's see. I'll give this one here this length, maybe from like, let me call this the datum. Call that the datum line here. And that's going to be, now notice everything above here, like this doesn't change length, this doesn't change length, this doesn't change length. So we can kind of measure everything from here. You know, there will always be this piece here. This is the same thing down around this side. That's constant, constant, constant. So I'll measure from here, let's say to this one here. I'll call this SC. And now notice that's going to cover these two pieces. Then let me do an SA maybe from here to here. Call that SA. That corresponds to this one here. My lines aren't too straight, but I think you get the idea. This is going to come across like this. And call this maybe SB over here down to this one. And let's see. Let me call these two here H. Like that. And now let's figure out if we can set up the equations. So let me set up the equation for the short cable. That's just one I have in black here. So let me put this over here. A short one. And so let's see what it has. Now we're going to have something for this small piece right here. Now since this is moving here and this is moving, notice we can't set up like a length of this because the two ends are both moving, but we can use the difference of these two. So in other words, this length right here can be described as SA minus SC. That would be this length right here. It's going to be SA minus SC. Of course, SA was measured from a fixed point, SC from fixed point, so we can do that legitimately. And then also that gives you this part. Then this length right here would be SA. And that's going to be equal to the length of the first cable. And then work with this. So we're going to have 2SA minus SC is equal L1. And take derivatives now. With respect to T. And of course, I'll leave off the extra step. So derivative of this is going to give you the velocity. And this is going to be 0 because remember our cable lengths are constant. Take a derivative of that, that's going to be 0. So now we actually have a relationship here. We can say that we can solve for VC. VC is equal to 2 VA. In other words, if we bring it over, be negative, multiply through by the negatives, so we have this. So now let's look at the long cable. See if we can come up with an equation for that. So the long cable will be this piece and this piece. So it's going to be like 2SC, right? This one plus this one, 2SC, then plus this length plus this length. So it's going to be 2H. Finally, plus SB. And that's going to be equal to the length of our second cable. That's going to be constant. Now, notice here as well, H is constant because this pulley is not moving and this pulley is not moving. So H is constant. So you could even leave it out, but I usually put in and it disappears when we take the derivatives. But just check ourselves here that we got everything SC plus SC plus H plus H plus SB. Looks like we got everything in the second cable. So take derivatives. Again, this is constant. That'll go away. And once again, you could solve this for one or the other. Let me solve it for VB equal minus 2 VC. And so let's see. Now, what are we given? We're given that A is changing at 5 meters per second. So we can use this equation here. Let me just give it a name and call this equation 1, equation 2. Use equation 1. And we have VC is equal to 2 VA. Again, VA was 5 meters per second. And now since it's going this way, this length is getting longer. So we'll keep that positive. So VC is moving at 10 meters per second. So VC is changed to 10 meters per second. And then finally, if we plug this into equation 2, we get VB is minus 2 VC. It's negative 20 meters per second. And let's take a look, see what that means. So VB is negative, so that means it's shortening. If it's shortening, if this length is getting short, means B is moving upward. So B moves upward at 20 meters per second.